Hello, everyone. We're going to get started this afternoon. Welcome back. My name is David. I'll be your session chair for the afternoon. So our first speaker, keynote for the afternoon, I feel like in this community needs very little introduction. Ian Goodfellow did his PhD completed in 2014 under Yoshua Bengio and Aaron Corville at the University of Montreal. He's perhaps best known as the lead author of the Deep Learning textbook by MIT Press, co-authored with his advisors, Yoshua and Aaron. And he's done very influential work on adversarial machine learning, both generative adversarial networks, which are a well-represented topic at this conference, and also on adversarial training and methods for mitigating and detecting adversarial examples. And he's going to give us a overview talk of adversarial machine learning. Please welcome the speaker.
Good afternoon. Thank you for coming. I'm glad to see everybody here. I'm going to try to give you a nice overview of how adversarial machine learning relates to several different research topics today. To start off by what do I mean by adversarial machine learning, I want to contrast it to more traditional machine learning. Most machine learning algorithms, not all of them, can be described basically as optimization algorithms, where we intend for the solution to the optimization problem to generalize. So optimization means we have some kind of cost function, shown by the z-axis on this plot, and some kind of parameters represented by the horizontal axes on this plot. We want to find the minimum of that cost function, or we at least want to reduce the value of the cost function to some very low value. In adversarial machine learning, we don't look to optimization as the mathematical language for our algorithms. Instead, we look to game theory. In game theory, each player has their own cost, and each player tries to reduce their cost, but the other player's choices also affect their cost. The simplest version of this that we can visualize on a slide is a minimax zero-sum game, where the two players' costs always add up to 1. In that case, you can represent it with a value function, as shown on the 3D plot on the right. To make this easy to visualize, I've shown just one parameter for each player. But you can see the value function is essentially this 3D surface where one player tries to minimize the value and the other player tries to maximize the value. If you look at cross sections through the cost function in terms of the parameters that each player can control, player 1 is looking for a local minimum and player 2 is looking for a local maximum. If they both find a point like that at the same time, it's called a Nash equilibrium. And we think of that as a solution to the game because neither player can improve their cost without controlling the other player. So that's the main difference between traditional machine learning and adversarial machine learning. Until about 2013, nearly all of us working on machine learning and presenting papers here at ICLR and similar conferences basically all had the same goal in common. We were all trying to get machine learning to work. In most cases, that meant we were working on supervised learning, either directly or indirectly. We worked in different application areas like speech or vision or text, but we were all really just trying to get machine learning working at AI level. Now we more or less have supervised learning working given a large data set, and we've seen a Cambrian explosion of different research topics, where people have moved on to adding new capabilities, like the ability to generate rather than just recognize inputs, or the ability to learn from reward functions instead of supervision, or adding extra properties like security or privacy. Now that we've had this Cambrian explosion of different research topics, I think it's useful every now and then to take a step back and look at the big picture and see how some of the same techniques can actually be leveraged by a lot of different communities. The first topic that I'll cover is generative modeling. The goal of generative modeling is to take a training set of examples and learn the probability distribution that generated those examples. The result can either be represented as a density function, or it can be represented as a machine that can generate new samples from the same distribution. Or in some cases, you can actually get both of those things. Today, I'll focus on the ability to generate new samples from the distribution. To illustrate how it works, I've shown here a training set of photos of celebrities on the left. This is the Celeb A data set. And on the right, I've shown 2 new imaginary celebrities created by a generative model. This is a progressive GAN that was trained on Celeb A. It inferred the distribution, and it created these people who have never existed before, but look as if they could realistically be celebrities who would be statistically the same as the real celebrities that we have today. The way that GANs work is actually via a two-player Minimax game. One player, the generator, creates images or other kinds of data. The other player, the discriminator, recognizes these images as either real or fake. When we train the two models, we see that there's adversarial competition over how to classify the fake samples produced by the generator. The generator tries to adapt the input to the discriminator to cause it to be misclassified, and the discriminator tries to correctly classify each of the fake inputs as fake. At the same time, the discriminator faces a non-adversarial component where it learns to recognize the real examples as real. Using the language of game theory, we can analyze this and find that there is a Nash equilibrium where the generator recovers the data distribution perfectly, and the discriminator can do no better than random guessing about whether the input is real or fake. In practice, we don't usually reach that Nash equilibrium, at least not with the algorithms we have today, but we do get to the point where we produce realistic samples. Since the session chair and some other people and I introduced GANs in 2014, they've improved rapidly. You can see that back in 2014, we were just barely able to generate small grayscale faces from the Toronto face database. And since then, other people have found better and better approaches that are able to generate high-resolution, high-quality photos. One thing that's interesting about this particular graphic is that the progression has been even more extreme than I can show you here. The image on the left of the Toronto face database sample is actually scaled up to make it visible on the slide. And the images on the right from 2017 and 2018 have both been scaled down dramatically so that they fit on the slide. So if you could actually see the true scale of these, the number of pixels has improved even more dramatically than this timeline implies. Generating faces was actually one of the easier challenges for generative models. Generating very many different categories turned out to be harder. It wasn't until 2016 that Augustus Odina and his collaborators were able to make a GAN that could produce recognizable samples from each of the different ImageNet classes. Even then, they were not very high-quality samples. But after we had the initial recipe, we made rapid progress until Big GAN was able to make high-quality, high-resolution samples from all of the ImageNet categories presented this year at ICLR. One thing that's especially exciting about GANs is that they make it possible to learn with less supervision than many other machine learning algorithms are able to do. Here we have a GAN that turns day scenes into night scenes. This approach is called unsupervised image-to-image translation. The way that we train this model is actually not by collecting pairs of day images and night images. If you think about it, it would be really hard to collect such a pair. You'd have to go out on the road in the daytime, see a bunch of cars on the road, take a picture of them, and then somehow or other get those cars to come back at night and redrive exactly the same trajectory. So maybe in some 3D rendered synthetic environments you could do it, but for real photos you can't. The GAN framework makes it possible to train the generator using feedback from the discriminator rather than from a specific target. So you can think of it as a way of telling the generator that there are many acceptable outputs rather than one specific target provided by the supervision signal. One of my favorite examples of unsupervised image-to-image translation with GANs is this cycle GAN video turning a horse into a zebra. You can tell that it would be really hard to gather supervised horse and zebra images because you couldn't really go out in the field and twist the zebra into the horse's position. You'd show up in the photo yourself while you were out there awkwardly trying to get the zebra to stand how you want it to stand. One thing that's interesting about this video is you can see some of the effects of bias in data sets on machine learning. Here it's very visually obvious that the background is changing along with the horse itself. The machine learning model has no way of understanding that the horse and the zebra are the parts we're interested in. So the background is actually changing from looking like a horse environment to looking like a zebra environment. Another thing that's interesting about this video is that it's generated one frame at a time, and the generator has no context about the time before or the time that's going to come after. So you can see that there are some artifacts in the video. In particular, watch when the horse turns its head at the end of his trip across the field. The zebra stripes remain stationary, and the zebra's head moves across them. So watch right now. Right now, the head moves across the stripes, and the stripes stay still. So can you actually improve that and make a video that's coherent? It turns out that to make a coherent video, you can actually generate the whole video sequence and feed it in its entirety to the discriminator, and then the discriminator can tell if the whole thing is coherent.
Manipulation and synthesis. In addition to synthesizing street scenes, we show our network synthesizing videos for other domains. For example, our network can transform edge map videos to videos of human faces. Here we show some examples of synthesized people talking. Our network can generate different people speaking given the same input edge maps. Note that the results are temporally consistent from frame to frame. Another example, we can synthesize videos of humans moving given pose information. For example, we can generate videos of people dancing.
This video of people dancing is created using a 3D model and then transforming the view of the 3D model into a view of the person dancing. You could also have gotten that 3D model from a video of another person dancing. So you could actually take a professional dancer and map their movements onto, you yourself, even if you're not a professional dancer. And that was accomplished by a team of researchers at Berkeley. That video showed how we can take a professional's dance moves and then the user of the generative system can put themselves into the video using their movements. It's also possible to go the other way around and take your own movements and your own design of a composition and have it translated into a photorealistic quality image. It means that we can remove the creativity from actually producing realistic pixels to composing a scene, and people who don't have the skill to be photorealistic artists in terms of the technical side can express themselves using the GAN to accomplish the realism that they would otherwise have to train to produce. This is called GoGAN.
This time, let's draw some mountains and trees. I first draw a grass-covered hill in the foreground, and then mountain in the back. More cloud will be nice. How about we plant a tree on the hill, like this? Note that the same label renders into two visually distinct objects, the trunk and the leaves of the tree. Now let's...
So the GoGAN image editor makes it possible to paint with pixels that say just which kind of class should appear at which point in the canvas, and then a conditional GAN that learns the distribution of our pixels given class labels per pixel, turns it into a completed image for you. So far, everything I've shown you with GANs has been purely digital, but one thing that has excited me recently is that GANs have started to make the jump into the physical world. The first example of this that I know of is 3D printed dental crowns from Glidewell Dentistry. Ordinarily, a dental crown has to be customized for the patient's mouth by a human technician, and it can take up to 2 weeks, during which time the patient has to wear a temporary crown. So it's actually necessary to perform two operations, first to install the temporary crown, and second to install the final one. With the GAN-generated crown, it's possible to get a high-quality customized crown and have it 3D printed immediately, so only one operation is needed. I'd be excited to see a lot more applications of GANs to the physical world. One application I'm really surprised hasn't happened yet, that I've been predicting for a few years, is GANs for fashion. We've seen GANs generating fashion images, but not actual clothing yet. And I know there's lots of people who'd like to put more pockets on their clothes and things like that. I hope that generative models make that possible soon. So how do all of these work? Some important recent advances in how they work include the recent BigGAN model really invested a lot in scaling up on TPU. And they found that rather than trying to stabilize the GAN, it's often better to train it with unstable hyperparameters and let it train until the last minute when it explodes and just save the last good checkpoint before the explosion happened. Some other recent advances include the style GAN from NVIDIA, where they incorporate style transfer techniques in the generation system itself. We can see an example of how the style transfer works. I show you three people's faces here. On the left, we have a starting sample. I want to emphasize even the starting sample is actually a sample from the GAN. We're showing what happens when we change the course style, but the image did come out of the GAN itself. So let's say we want to style transfer on the course style of a different person, such as a child. The person in the middle is a child that was also generated by style GAN, and we're going to take the course style of the child image and apply it to the image of the adult on the left. The output is the image on the right, which is a child version of the person on the left after transferring over their course style. Overall, style GAN makes it possible to represent a face in terms of course style, where it captures things like age and gender, medium style that captures some of the face geometry, and fine style that captures things like the positions of individual hair or wrinkles in the face. One thing that's been kind of disappointing about GANs is that we think of them as an unsupervised learning algorithm, but actually most of the results I've shown you required supervision. To get really good samples from ImageNet categories, we actually have to train with class labels. Some recent work from Brain Zurich shows that it's actually possible to reduce the number of labels needed to get a good image generation GAN. In particular, they were able to bring the number of labels required to match BigGAN down to about 20%. About 10% of the labeled data, rather than requiring a label for every single image. That's generative modeling. The next major research area where adversarial machine learning has been useful is machine learning security. So far, machine learning has been very effective on naturally occurring IID data, where all the data is drawn from the same distribution as was used at training time, and all the examples are generated independently from each other. If we want to make machine learning secure, and we want to make it so that an attacker can't intentionally cause the model to output a class of the attacker's choice, it's necessary to relax those IID assumptions. We've seen many times over that it's very easy to do things like subtly modify an input and, for example, change this panda into a gibbon according to the model. So how can we actually resist this? We also need to remember that it's possible for attackers to use very strange inputs, such as graffiti on a stop sign, or just present objects in a context different than the way that we see them in the training set. For example, this apple is recognized by most current commercial object recognition algorithms until you put it inside a mesh bag, and then even though it's not fully occluded, it looks different enough than it did in the training set. So relatively simple real-world modifications are enough for the IID assumptions to be broken, and we need to think about all of these things. We don't really have a full solution yet, but so far a lot of the best solutions have been based on adversarial training. The idea behind adversarial training is, again, like with the GAN, to look for an equilibrium to a game. You can think of one player as the machine learning model, and it's trying to minimize its error rate as it classifies different inputs. The other player is the attacker, who tries to optimize to maximize the failure rate of the machine learning model by changing the input to inputs that will be misclassified. Another research area that I think has not been explored as much as I would have thought is model-based optimization. And here, adversarial machine learning will be very relevant. The basic idea behind model-based optimization is that if you want to maximize some function that you don't directly have access to, you can instead learn a model for that function and then maximize the model's estimate of that function. So let's say we wanted to make a really fast car. We could make a model that looks at a blueprint for a car and then predicts how fast that car will be able to drive. As we improve our blueprints, we can move from something like the Model T to a really fast supercar. Unfortunately, it's actually hard to do this today. In a lot of different scenarios, if you build a model and then search for inputs that are predicted to perform very well, you'll actually get an adversarial example that the model thinks will perform very well, rather than a high-quality example. I think that some of the techniques from the GAN literature and from the adversarial example literature could help to unlock some of the potential of model-based optimization. We have actually seen some applications of model-based optimization already. The best results that I know of are for designing new genes. You can think of a gene as a sequence of DNA characters that describes a sequence of amino acids. And when you convert from the DNA sequence to the amino acid sequence, you get a protein. The protein is just a molecule that actually does something in a cell. And to design new medicines, what you usually want to do is design that protein so that it will bind very tightly to a specific receptor. That's just a part of the cell that can accept these molecules and either gain or lose functionality based on having a protein bind to it. So you can use model-based optimization to maximize the binding affinity of the protein by changing the DNA base pairs. A few different labs have explored different techniques using adversarial machine learning to design proteins that bind very well in simulation. I think this work will probably move on to actually making proteins that bind well in reality soon. And then we can start to see adversarial machine learning used to design useful medicines. One research area where adversarial machine learning has always been relevant is actually reinforcement learning. In fact, you could say that the original machine learning was a form of adversarial machine learning. One of the first machine learning projects that I'm aware of was Arthur Samuel's checkers playing agent. At the time that he made this in the 1950s, most people believed that a computer could not do anything except what it had been explicitly programmed to do, and his project demonstrated that that was not actually correct. He wrote a program to play checkers against itself and learn from the checkers games that it played against itself. Because it had this repeated self-play experience, it eventually learned more about checkers than he himself knew, so his own creation could beat him at checkers. And that effectively proved by example that you really could get computers to do things that their programmers could not explicitly tell them to do. This self-play approach is essentially a form of the Minimax game that in recent years we've extended to other things like defenses against adversarial examples and extended to GANs. It's a relatively simple form of the game because it's perfectly symmetric. The same player is playing both sides. And a lot of the recent advances in this field have actually been moving to non-symmetric games and thinking of how to do things other than just win the game. For example, GANs, it's not so important that we're winning or losing in the game. It matters that we're producing high-quality samples as a side effect. We've seen that self-play continues to be a really important strategy for reinforcement learning, though. Things like AlphaGo and OpenAI's defense against the ancient spot are both based on self-play. And so are the sumo wrestlers from OpenAI that learn behaviors like ducking and faking out their opponents without needing to be told that those are useful behaviors. They just learn them from self-play. It's also possible to make adversarial examples for reinforcement learning. Sandy Huang showed that you can make adversarial perturbations of frames of Atari video games, and you can even hypnotize the agent and make it perform worse in the future. So you can show it a perturbation, and then it doesn't make a mistake immediately, but a few frames later it makes a mistake because the perturbation encoded something in its recurrent memory. A major challenge in reinforcement learning is to encode good reward functions that describe the behaviors that we really want. It can be hard for a programmer to design something by hand that really encourages exactly the behaviors we want without encouraging side effects. One way out of this situation is to learn the reward function. And a recent project from DeepMind showed that it's possible to use a GAN-like model to learn a useful reward function. In this case, what they want to do is draw specific characters on a canvas. The characters are drawn from the Omniglot dataset, which contains symbols from many different languages. This little curly symbol here is one of these Omniglot characters. What we want to do in this case is have the robot paint that character on the canvas. We can't just use a reward function like mean squared error between the photo and the canvas, because the canvas is presented as a perfectly black and white bitmap and is viewed perfectly axis on. The canvas is viewed at an angle, and because it's a photo, it has lighting effects and things like that. You're never going to get the photo to exactly match the bitmap input. But you can learn something resembling a GAN discriminator that tells you how close you are to accomplishing the goal, and then follow the gradient of that discriminator instead of the original mean squared error loss. And then that can result in the robot successfully painting the figure on the canvas. Another important research topic is extreme reliability. A lot of our machine learning algorithms can get up to something like 99% accuracy, but for a lot of applications that isn't good enough, and in the long run we need to figure out how to make them even more reliable. If we were going to use machine learning for something like air traffic control or a surgery robot, you really want it to be more robust than the current models we have. I think that adversarial machine learning can be a useful framework for eventually tackling these problems. And the reason is that adversarial machine learning is about solving for the worst case, where you take a really messy real-world problem, and instead of trying to model specifically how the real world is messy, you just say, what if all of the messy factors were as bad as they could possibly be? Because modeling the worst case is often theoretically simpler than modeling the real-world case. I've tried to illustrate that with a graph here, with a blue curve showing worst case performance and a green curve showing average case performance in a hypothetical problem. The green curve is really messy and unpredictable, but the blue curve is relatively smooth. You could imagine that we could optimize the blue curve, and then we're guaranteed that the green curve will be even better than whatever we got by optimizing the blue curve. This kind of worst case analysis and worst case design is a common engineering principle that's worked well in other disciplines. One example is distributed systems. At companies like Google that implement large file systems using multiple machines networked together, a lot of that stuff is based on what's called Byzantine fault tolerance. The basic idea is that instead of modeling all the ways that individual machines can crash or drop packets or send random packets, you can design protocols that will work even if some of the machines were controlled by a malicious adversary who does the absolute worst thing at each moment. So a lot of distributed file systems are based on protocols that are designed to be robust to an adversary who can crash a machine at the absolute worst time, or drop the absolute worst packet, or send the absolute worst fake packet. And that's how we have our modern internet economy. I think we can possibly get a similar result for machine learning using adversarial techniques to design and verify systems to be robust. We're already starting to see a little bit of this. There's a technique called ReLUplex that was originally created to verify that machine learning algorithms are robust to adversarial examples, and it's been used to analyze and verify air traffic control systems. Another really important research area is the label efficiency of our models. Today, supervised learning works really well, but you need to have a very large amount of labeled examples, and a lot of the time that's just not feasible. It can be expensive to gather the labeled examples. It can also have other kinds of costs besides money. For example, if you're working in healthcare, to label some of your examples, you may need to have patients undergo painful or invasive and risky tests to find out what the true state of your patient is for the machine learning model to predict. So it's important to be able to bring down the number of labels that we need. One approach using adversarial machine learning to improve label efficiency is to actually take a GAN discriminator and train it as a classifier instead of just a discriminator. When we use a discriminator in the GAN framework, it really only has two outputs. It can say that the input is real, or it can say that the input is fake. In the semi-supervised learning framework, we can actually extend it to have as many outputs as we want our eventual classifier to have, and then we give it one extra input saying that the input is fake. So for example, if we want to train a model to recognize cats and dogs with very limited label data, we can make a discriminator that has three output classes: real cat, real dog, and fake. It can then learn from three different sources of data. One source of data is fake data coming from the generator, and we train the discriminator to say that that data is fake. Another source of data is labeled real data, like we would usually use to train a classifier. And there, as with a regular classifier, we just train it to output the correct label. If we see a cat, we say output real cat. If we see a dog, we say output real dog. And then there's a third class of data that we can learn from, which is really important. We can actually learn from unlabeled real data. And when we see unlabeled real data, we don't know whether it's a cat or a dog, but we can just maximize the sum of the probabilities for all of the real classes. So we can say we want to increase the logarithm of probabilities for classification and a domain recognizer network that examines the features. The domain recognizer network examines the features and tries to predict which domain they came from. So for example, you could train on Viper and PRID, and the domain recognizer tries to tell whether the features were extracted from Viper or extracted from PRID. Then the feature extractor learns separately in this adversarial game. It tries both to learn features that are good for classification, but also to learn features that confuse the domain recognizer so that all the domains become equally probable. This works well if you want to train on Viper and PRID and then deploy to CUHK. Another really similar idea is called professor forcing. Professor forcing is designed to solve a problem with generating samples using recurrent nets. When you train recurrent networks on, for example, text, you feed in a full sentence of words and condition the recurrent net on each word in the sentence. So when it's estimating the probability distribution over word I, it's conditioned on real words 1 through I minus 1. So it only ever sees real data when it's guessing the next word. It never gets its own outputs fed back in as input for the next time step. After it's been trained that way, when you deploy it to actually generate new text, it will generate the first word, and then it gets conditioned on the first word to produce the second word. So it starts to see its own output as input. And if the output from the recurrent net doesn't match the distribution of real words exactly, then it starts to wander further and further away from valid sentences. Early on, it might pick a few strange words, and then it becomes even more strange because it's now producing words given unusual inputs. Professor forcing is an idea that essentially applies the domain adversarial network idea to recurrent nets, where one domain is the recurrent net clamped to real data, and the other domain is the recurrent net in free running mode. We use an adversarial critic to make sure that the statistics of the recurrent net's hidden units are the same, whether it's run on real data or run in free sampling mode. One of the most popular domains that we want to bridge the gap between is simulated data and real data. One way that we've seen this work is actually using a GAN to enhance synthetic data and make it look more realistic. This is useful because if you want to learn to tell where a person's eyes are looking, it's actually hard to gather real data with labels about where the eyes are pointed, but it's easy to gather lots of unlabeled pictures of eyes with no direction associated with them. It's also easy to make a 3D model and render it with the eyes pointed in directions that you know where they are because you positioned the 3D model yourself. If you just train a model on the synthetic eyes, though, it won't work very well in real photos. So what you can do instead is train a conditional GAN that takes the eyes and makes them look more realistic. So then you can take synthetic 3D rendered eyes with known direction and refine them to appear realistic, and now you have both properties in one sample. You have both realism and a labeled eye gaze direction, and you can then train your model to deploy in the real world. So that's one way of bridging the gap between synthetic and real. We saw another example of more or less the same strategy around the same time in Google's GraspGAN. The idea behind GraspGAN is to train a robot arm to solve grasping tasks where it can pick up objects in this tray. GraspGAN uses synthetic data rendered from a simulator, but then uses a GAN to turn the synthetic images to look realistic. And the value of this data is very high because we get both a per pixel class segmentation mask, shown on the right, and a relatively realistic image, as shown in the middle. If we just used real photos, we wouldn't have the per class segmentation mask unless we had people label them explicitly. And if we just used synthetic data, we wouldn't get the realistic appearance. GraspGAN is able to actually perform better on real data using synthetic and real training data put together than if it could use only real data or using only simulated data to train. A more recent approach to generalizing from synthetic to real data is called sim to real via sim to sim. The model is trained to deal with many different simulated conditions, and as long as there's enough diversity in those simulated conditions, it can then deal with the real world. In particular, a GAN is trained to map from randomized simulated domains to canonical simulated domains. So by randomized simulated domains, I mean images generated with the simulator configured to use really weird textures, like shown in the upper left. And then by canonical sim, I mean images like the one in the upper right, where the simulator is set to use relatively flat textures with one specific color for each part of the robot arm. After the GAN has been trained to convert images from very many different randomized simulated domains to the canonical simulator, we can then use it to process the real world and turn the real world into images that look like they came from canonical simulation, as shown in the bottom row. Because we now have this conversion layer that can turn any image into a canonical image, it's possible to train the robot policy only on the canonical simulated images. And then when we deploy it in the real world, the policy never actually sees a real image. It only sees canonical images that were converted on their way in from the camera. And it's actually able to learn to grasp without ever using any real data. You can, of course, also improve its performance by using real data in the training. It's also important to study fairness, accountability, and transparency. One approach to fairness is if you want to make sure your model ignores a certain variable, you can use a technique similar to domain adversarial learning, where instead of trying to make it impossible to recover the domain from the features, you make it impossible to recover a sensitive variable from the features. There are multiple definitions of fairness, and this approach doesn't necessarily satisfy all of them. It also doesn't come with a provable guarantee that you've converged to a Nash equilibrium or the sensitive variable has been entirely removed, but you can more or less encourage representations to ignore variables that you think should not affect a decision. A lot of the machine learning literature has recently focused on interpretability. Part of the reason this is important is that we want to be able to tell how machine learning systems are working so that we can make sure that they're fair. I think, unfortunately, a lot of the interpretability techniques we have today imply that the systems work better than they do. And I hope that we see more talk between adversarial machine learning people and interpretability people. We see a lot of systems that examine modern convolutional nets and say, look, they classified the dog as a dog because of the dog pixels, and they classified a cat as a cat because of the cat pixels. So it looks like they're working, but then at the same time, you can take that same model and turn the panda into a gibbon without changing any of the panda pixels significantly. So I hope we can get interpretability tools that are more aware of these kinds of failings. I also believe that as we make models more robust, they'll become more interpretable. We've seen that since about 2015 with some of the first work on adversarial examples that we did at Brain. The image on the left is a linear model, which you might think is interpretable because it's linear. It turns out people have really bad intuitions for how linear models behave in high-dimensional space. Everywhere you see a yellow box, we have successfully turned the input into a different class. So as you read left to right, top to bottom, the first yellow box is where the 9 has become a 0, according to the linear model. The second yellow box, it's a 1. The third yellow box, it's a 2, and so on. So even though this model is linear, it's very hard to convey to a human that it has all of these mistakes baked into it. The model on the right is a robust model, where when we try to maximize the probability of the 0 class, we actually get images that look like zeros. When we try to maximize the probability of the 1 class, we get images that look like 1s, and so on. So even though the model is not linear anymore and might seem like it's harder to understand, the way that it behaves under optimization of its input is actually much more consistent with human intuitions. I'm not saying that this is anywhere near formal enough to have a real fairness tool, but it does give me some optimism that studying robustness will make the interpretability problem easier. And then lastly, I think that adversarial machine learning can actually tell us a lot about ourselves and how our brains work. You can think of adversarial examples as bugs in machine learning models. And we know that the human brain has a lot of bugs like optical illusions. But so far, the optical illusions for humans have been different than the optical illusions for machine learning algorithms. What if we could start to find some bugs that we have in common? Well, recently, some of my collaborators and I found that we could actually make images that fool multiple convolutional nets. And if you get enough convolutional nets participating in this game, and you give humans a time limit, we can actually make images that fool time-limited humans. The picture on the right of the spider is usually correctly classified as a spider, but if we make an adversarial perturbation of it, as shown on the far right, humans with a 200 millisecond time limit will most often classify it as a snake. And then if we take a more extreme version of this approach and allow it to make bigger changes, we can actually take this cat and make it look like it's a dog, even to a human with no time limit. We don't know for sure whether the dog is really a dog and we've changed it too much and we've changed the true class, or whether we've managed to fool even the time-limited human. These are only really the first results about adversarial machine learning for neuroscience, but I think that now that we've seen that there's a little bit of signal here, there's a lot more to explore, and we can learn a lot about the human brain by finding the similarities and differences between bugs in machine learning and bugs in humans. Thank you for listening to my talk. I think I have a few minutes left for questions.
Thank you very much, Ian, for the talk. Questions? There are microphones. Do we have any questions?
Yeah.
Okay.
Here.
Yeah.
I was wondering, I've really noticed also actually in your talk that there's quite a difference between how much interest there is in adversarial networks in academia versus in industry. I see very little use of them in industry. Do you have any feeling of why this is and how it can be solved?
A lot of the companies that are working on machine learning in industry are not really doing image generation stuff. But companies that do work on image generation like NVIDIA and Adobe have been a lot more enthusiastic about them. I don't necessarily think of it as a problem to solve. just if your business isn't image generation, then I don't see a reason to use that particular tool.
Okay. Well, because you mentioned so many other applications today.
Oh, I'd say like most of the things I talked about were things like machine learning security, where there's other applications. I think for things like model-based optimization, then people will need to use adversarial techniques, but maybe not necessarily GANs. There's a lot less work on model-based optimization right now. I think partly just that's more complicated and less likely to turn into a product immediately than some other things like classifiers or recurrent nets.
Okay, thank you.
Dima?
So I really like the example with the apple in the mesh bag that confuses the classifiers. So you said that adversarial training could help us with examples like that. Can you please clarify? Because I can't really imagine, again, generating an apple in the mesh bag.
Well, so I guess I'm illustrating that the problem is really hard and it's really far from solved. I don't actually know how we're going to solve the apple in the mesh bag. If you wanted to think that you would get there with just adversarial training, in that context, I'm thinking of adversarial training in the sense of optimizing over actions available to the attacker in a threat model. So it's a little bit different than the GAN version. You can imagine if you want to specify a threat model that includes putting mesh bags around things, then using a GAN to represent those actions might be a useful way to tackle it. But I think we're very far from actually demonstrating anything like that.
Thanks.
Okay, we have time for one more. Yes.
Yeah, hi. Generative models, some argue GANs in particular, have poor evaluation metrics, such as FID or inception score. What do you suggest, like, what avenue do you suggest that we think about how we evaluate our generative models moving forward?
Yeah, for a lot of machine learning algorithms, evaluation has gotten really hard. And the gold standard is really to think about what's the downstream task that you want to use them for. If you're hoping to use the GAN for semi-supervised learning, then you can measure accuracy of the classifier at the end. If you want to use the GAN to generate imagery that pleases humans, you can use human evaluation as the property at the end. If you're doing something else, then pick a metric specific to your application area. In a lot of cases, it's not that the metrics are necessarily bad, it's just that there's more than one property the model can have, and you're only going to evaluate one of those properties at a time. So like likelihood measures how much do you put probability mass on the test set, but it doesn't tell whether you've over-memorized the training set. Things like Fréchet inception distance can tell you how close you are in terms of moment matching to the training data, but it doesn't really tell if you've put any mass on anything new on the test set. A lot of the time people just plot curves where they show trade-offs between more than one metric, and that can give you some idea of how it might perform on different downstream tasks. But I don't think there's any real perfect solution. I think it's mostly that we've moved to more complicated models that have more than one performance characteristic, and we can't expect to embed it all in one number.
Cool, thanks.
Let's thank the speaker once more.